Hello everyone. In this video, we are going to discuss about the third law of thermodynamics. Third law of thermodynamics. So, third law states that at absolute at absolute zero temperature, what do you mean by zero temperature? It's not 0 degrees Celsius. It's not 0 degrees Celsius. It's actually 0 Kelvin is the absolute zero temperature. Because in the standard systems, zero temperature is referred as 0 Kelvin. So at this temperature, the entropy at this temperature, entropy of a system which should be not every system which should be pure and perfectly crystalline must have an entropy S equal to 0. So, what the statement interprets is at 0 degree Kelvin, the entropy of the system, which is pure and perfectly crystalline substance, must be 0. So, how we can prove it? Let's see how we can prove the theorem. So, consider a perfect crystalline solid without any impurities. All the atoms are identical. What I said previously about entropy, entropy is the redistribution of energy among the system, among the microstates. So, entropy depends on the number of different ways of arrangement of atoms in different energy levels and its redistribution within the microstates is called entropy. So, from the third law, we can say that entropy is directly proportional to the number of ways of arrangement. So, we can represent it as omega. So, this omega is nothing but number of ways of arrangement of n number of particles in a system. So, let's say this is the formula for omega. So from the formula what we can say, n is the total number of particles, n is the total number of particles in the system which should be identical and distinguishable. Identical and distinguishable. N naught, N1, N2 and the N are the number of particles in the energy states or microstates epsilon 0, epsilon 1, epsilon 2 up to epsilon n respectively. So from this statement we can say that entropy is directly proportional to the number of ways of arrangement of the microstates, that is given by this formula. So now we need to identify the number of ways of arrangement in the perfect pure crystalline solid at 0 Kelvin. So at 0 Kelvin what will happen? All the atoms comes to a rest position, which is the minimum energy or lowest energy state. So in this state all the atoms in this state what we can say, all the atoms are identical. As we say, it is pure crystalline. So pure means we won't have any impurity, so it is all the atoms should be identical only, there should be no mixture in this system. So all atoms are at a rest position, which means all atoms have same equal amount of energy. So if all the atoms are identical and have same equal amount of energy in all degrees of freedom, that is among x, y, and z direction in translation or rotational or vibrational motion, all have the same equal amount of energy. That is the lowest energy, which means it won't have any energy among those translational or rotational or vibrational field degrees of freedom. So in this way, how many ways we can arrange the particles? We have only we have many particles, but we have those many particles which are identical and distinguishable is not available here. We have identical and indistinguishable, so we cannot differentiate each particles. So if we don't have any differentiation, we can consider it as only one state having the identical and indistinguishable configuration. So we have only one state, so only one microstate. In that only one microstate, all the atoms are arranged. So which is also one. So finally, omega is equal to one. One factorial is also one. So one divided by one is equal to one. So I said S is directly proportional to omega. So to remove the proportionality constant, we can add the Boltzmann constant K. So if we here we have only one microstate and only one configuration. In this configuration, we can calculate the entropy as just K, and it is very easy. But if you have n number of n number of microstates, uh, and its factorial value will go beyond the limitation of computation. So for that we need to add the logarithm, which will scale down the computation and makes us easy to compute the value. So here k value is Boltzmann constant, same. Log of omega is 1. So log of 1 is 0. So at 0 Kelvin, entropy of the system is also 0. This is how we can prove the third law of thermodynamics. Now we will see an example problem for the third law of thermodynamics. So let's say the question is like this: the correct entropy for six identical particles with their occupation number zero, 1, 2, and 3 in four different microstates. So here we need to find the correct entropy. The options given are: A is K of log 6, B option is K of log 12, C option is K of log 60, D option is K of log 720. So pause here and try to compute the value, and then again watch for the solution. So now we will move on to the solution. How we can calculate it? We have the systems of six identical particles. Six particles we have it. Those are identical and distinguishable. So we have the n factorial equal to 6 factorial. N factorial is 6 factorial. Now again, the number of ways each state, that is n naught, n naught factorial is 0 factorial, n1 factorial is n1 factorial is 1 factorial, n2 factorial is 2 factorial, and n3 factorial is 3 factorial. So here factorial we have to mention because n naught may have zero number of particles, or may also have one atom here, and here nothing, zero. Here also it can have one atom or nothing, or two atoms. Here it can have 0, 1, 2, 3. So here all possible values are possible in these states. So we have to take the product of these factorials, and we have to put it in the denominator. So now we will calculate the omega. Omega is equal to n factorial divided by n naught factorial into n1 factorial into n2 factorial into n3 factorial. So entropy. So here we will compute the omega value. N factorial is 6 factorial divided by n naught factorial is 0 factorial into 1 factorial into 2 factorial into 3 factorial. So 6 factorial, how we can write 1 into 2 into 3 into 4 into 5 into 6. 6 divided by 0 factorial is 1 into 1 factorial is 1, 2 factorial is 1 into 2, and 3 factorial is 1 into 2 into 3. So finally 2 into 3 6, 6 into 4 24, 24 into 5 into 6 30 divided by 1 into 2, 1 into 1 1, 1 into 2 2, 1 into 2 2, 2 into 2 4, 4 into 3 12. So we can cancel here and it becomes 2, which is finally equal to 60. So omega is 60. So S is equal to K log base E omega K into Boltzmann constant into log of omega value is 60. 60 base E. So finally the solution is S is equal to K log base E into 60. So this is the final answer for the entropy of the system. So the correct answer is option C. So this is how we have to understand the entropy of the system. So entropy of a universe will always increase. It cannot decrease because from the Big Bang to till the date, entropy is increasing because the particles are redistributing themselves according to Boltzmann statistics, and the graph is diverging. So this divergence causes the entropy to increase, and the universe is becoming cold, reaching its least energy by emitting the radiation. So now it is in the now the universe is releasing the energy in the state of cosmic microwave background. Soon it will become sooner or later it will become a radio wave, and finally the atom will cease to freeze again, and we may not know what will happen in the next era. So now I will give you a question to think and brainstorm yourself to understand the entropy. Let's say you are stretching a rubber band, stretching a rubber band. What would be the entropy of the system? Will it increase or decrease? So think about it and put your answers in the comment. Thank you for listening. See you in the next video.